Okay, with Kirchhoff's rules, we're going to try a little bit of a different approach in circuit analysis. This is going to be different from reducing parallel and series resistors into equivalent resistors. And actually, Kirchhoff's rules, although it's a little more challenging, it's more powerful in the types of circuits that we can analyze. Kirchhoff's rules were developed by Gustav Kirchhoff, who was very important for spectroscopy. He actually is famous for the analysis of some of the spectral lines that we see in sunlight, for instance, the absorption lines. But his rules for electronics is also very, very important into understanding how they're going to behave. He has two basic rules. The first is the rule for voltage. It says when you go around a circuit, when you go around a loop in a circuit, you're always returning to the same point in terms of what the voltage is. So therefore, if you start at 10 volts and then go around resistors and EMFs where the voltage goes up and down and up and down, when you return to that 10 volts, the change in voltage must be zero. So therefore, any difference that I see in voltage throughout the circuit, by the time I go back to the original point, is going to be zero, and therefore we can use this to try to determine what unknown voltages might be, use that to calculate current. Likewise, the junction rule is also based on a very important rule, and that's conservation of charge. You can't have more current coming into a junction where wires connect than you have leaving that junction where wires are taking the current away. So basically, conservation of charge. No place can you have current arriving out of nowhere and disappearing into nothing. So again, we're going to analyze different circuits based on this junction rule, based on the loop rule. And again, it's a little bit more complex, and it takes a little bit more planning than we had with the series and parallel analysis. But as we'll see, it's very powerful. It allows us to actually solve some basic circuits which we can't do through series and parallel equivalent resistors. This happens when you have multiple EMFs, which are in series and parallel with different resistors, and specialized circuits such as bridge circuits. So it's actually a more general tool than what we used before in doing some of the analysis. So once again, junction rule, what you're going to look at in the circuit is you're going to look at how different wires are connecting, and then you're going to sort of guess or estimate how the current should flow. So for instance, at one junction, I'm going to say the current comes in here, goes out here and here. So I must be equal to I2 plus I3. Now, sometimes you will get a case where you pick a direction for a current that turns out to be wrong. No big deal. Your equations still give you an idea of what's really going on. And what will happen is when you solve simultaneous equations, some of the currents will come back as negative. And what that just means is the direction that you've chosen is just in the opposite direction. So for instance, if I solved something and I saw I1 was negative, that would tell me that I1 was going out of the junction with I2, and I3 would be equal to I1 plus I2, rather than I1 being equal to I2 plus I3. So again, we are going to apply these loops. We're going to apply this junction rule. We're going to get a set of different equations. Typically what is unknown here is the current, and we're going to use this combination of equations and solve them simultaneously to find the unknowns. So you really need as many equations as you have unknowns. Typically, again, that means the number of currents that you have to have an equivalent number of independent, it can't be trivial, independent equations to solve for that. So for instance, when we're applying the loop rule, we have to be careful as to which way the current is going. For instance, if I'm following a loop and it's going from A to B, the loop is going to go around the whole circuit, but at one point if it's going from A to B, the voltage difference from A to B, if it's going with the current, okay, remember current goes from high voltage to low voltage, high voltage to low voltage means delta V will be negative as it passes through the resistor. Okay? It's not going to go from low voltage to high voltage. Their current's going to go with the drop in voltage. So with current in a resistor means that delta V is equal to negative IR. Going against the current, again from A to B, sort of like going upstream, you're going to a higher voltage. Going against the current, delta V from A to B becomes positive IR. So very important to notice that it's a little counterintuitive because you think, oh, I'm going with the current, it's going to be positive. No, it's going against the current, which is positive for a resistor, and going with the current is negative. All right, so looking at EMFs, sometimes you'll have multiple EMF sources. Again, look at what the voltage is doing. If you're going from the negative terminal to the positive terminal of the EMF, as you go from A to B, then we're increasing in voltage. Negative to positive is an increase. If we go from positive to negative, then we're dropping in voltage. That means delta V, the change in voltage, is going down. So therefore, we have a negative EMF there. Keep that in mind, again, when you're analyzing things. So again, we'll come up with junction equations for the current going in, the current going out. We'll come up with loop equations for the voltage going around one complete circle. Remember that the loops themselves don't pass through every single circuit element most of the time. They only pass through to return to the original point. So there's several loops that we can create, and that's good because it allows us to create multiple equations. Let's take a look at an example of a single loop. Okay, we have A, B, C, and D, which are different points. A and B go across the EMF. C and D go across the resistor. Now, I can choose two different loops here. I can have a loop that goes clockwise, or I can have a loop that goes counterclockwise. Now, in choosing the direction of the current, it's fairly obvious where the current's going to go. The current is going to go from positive to negative. I only have one EMF source, so it's going to push the current in the direction that my loop is going. Now, in looking at the voltage drop from B to A, okay, if I go from B to A against the current, that'll correspond to a positive EMF. If I'm going from A to B, that's a little bit backwards, what we have right here. So our change final minus initial, we're going with the current. The EMF is pointing in the same direction. It's going to be a positive right here. From B to C, we're just going along a wire. There's no resistor in EMF, so that's 0. From C to D, again, D minus C, as we go with the current, we're going from a higher voltage to a lower voltage. That means delta V is negative. So therefore, if delta V is negative, the potential drop there is negative IR. All right? And then finally, from D to A, D minus A, the voltage difference is 0. So going around this full loop right here, and oftentimes we ignore the wires. Like, I didn't have to write this, I didn't have to write this. I would just write the EMF, the voltage drop across the resistor, set them equal to 0. And very simply, this is something we already knew. The EMF is equal and opposite to the voltage drop across the resistor. They add up to be equal to 0. Therefore, I is the EMF divided by R. Straightforward. In fact, if I chose a loop that went in the opposite direction, all right, now we're going this way, we're going counterclockwise, our EMF would be negative, and going through the resistor, we'd go from a lower to a higher, that would be positive. So we'd have positive IR, negative EMF. Again, we put them in this equation, the result's the same. So two different loops, yeah, they're just going in opposite directions. Same result, it doesn't matter oftentimes what direction you choose the particular loop in. Okay, it's just going to switch your signs around, you're going to get the same outcome. We can do this to resistors in series. Here we apply basically the junction rule says what? The current that comes from the battery, I, is the same that goes through I1, I2, I3. They're all the same. So once we find I, we found the current. Okay? The loop rule, go around, as we go through each resistor, we get our EMF first of all going this way, then the voltage drop across the first resistor, the voltage drop across the second resistor, the voltage drop across the third resistor. Okay? All these add up to be equal to 0. We solve for this, and once we solve for this, I times R plus R2 plus R3. Again, it's all set to equal to 0, so we solve for I there. We see that I is equal to E divided by R1 plus R2 plus R3. This is the same exact result we got before, where we got the EMF over the total resistance. And again, that shows that the equivalent resistance of these three series resistors is in fact just the sum of each individual one. So there is, Kirchhoff's rules for series resistors, just basically showing that this is equal to this. Works. And again, here's just rewriting the same thing. Here was our result from putting the three in series. Here is a result from reducing this to a single one, and we can show that the two are equivalent. Okay. For parallel, we can do basically the same thing. We know for a parallel circuit that the EMF is the same no matter where you go. Go up E, drop V1. Go up E, drop V2. Go up E, drop V3. So all of these are going to be equivalent pretty much by the loop rule. If we now do the junction rule, the sum of the currents going into a junction is equal to the sum of the currents going out. So the current that goes to A branches off to I1, I2, I3. All right? So the total current is equal to I1, I2, I3. We know by Ohm's law, I is equal to V divided by R. Making that substitution there, we get this equation. Okay? And again, we apply the loop rule. If we go through an equivalent resistor, okay, we replace these three parallel ones with an equivalent resistor, okay, we know I is equal to V divided by Req. I is equal to V over 1 over, the sum of the reciprocals. All right? So very, very simply, this gives us the same result that we already knew for parallel resistors. So interesting to analyze series and parallel using Kirchhoff's rules, but again, we're just getting the same results that we got before. All right, let's actually apply Kirchhoff's rules to something and show that we know it can work. Again, the junction rule, what goes in must come out. The loop rule, the total change in voltage across a continuous loop is going to be 0. Now, what I've chosen here is I've chosen a circuit where we have two resistors in parallel. They're connected to a resistor in series. So I'm going to choose I1 as being the current that leaves the battery, passes through this resistor, and then branches off I2 and I3 to go through the 5 ohm and the 9 ohm resistor. That's going to give us a very simple result. I1 is equal to I2 plus I3. What goes in? I1 must go out. I2 plus I3. We'll then do loop rules. We actually can come up with 3 different loops. We can do a small loop here. We can do a big loop going all the way around the outside. I'm not going to do that one. Or we can do another intermediate loop that goes like this. So in actuality, we have 3 unknown currents. We can come up with 3 loop equations and 1 junction equation. We have more than enough equations to solve for this. Let's see what we get. Okay, again, going into this node, C, I1 is equal to I2 plus I3. Or if we look at D, going out of D, we have I1 coming out, I2 plus I3 going in. So that equation is really the same equation. We're not getting any new information depending on where we're looking at that junction. We will start with that as being the first equation that we're going to use. Okay, now let's do the big loop. We're going to do this loop going all the way through these two resistors. Okay, we're going counterclockwise, so we're going to go through this EMF first, pass through the 4 ohm resistor, pass through the 9 ohm resistor, and avoid the 5 ohm resistor. As it goes through the 4 ohm resistor, it's still I1. As it goes through the 9 ohm resistor, the current becomes I3 because I2 is branched off where our loop doesn't go. So, in the big loop, we have 6 volts from the EMF, okay? We pass through the 4 ohm resistor. Look, we're going with the current I1, so the voltage is going to drop, it's going to be negative. It's I1 times 4 ohms. Now we're going to go through this 9 ohm resistor, I3 times 9 ohms, okay? And that's all the voltage drops that we have and all the voltage changes. All those add up to be equal to 0. So now we have a relationship between I1 and I3. We can simplify this. Let's simplify this to solve for I1, because I'm going to make a substitution later on. I'm going to solve for I1, so I'm going to move everything over to the other side. I'll move this to the other side. Divide both sides by 4 ohms. We get 6 volts divided by 4 ohms. Okay? This is moved to this side. Now it's I3 times 9 ohms divided by 4 ohms. And finally, here's our next relationship. I1 is equal to 1.5 amps minus 2.25 times I3. So we have 2 equations so far from one junction and also one loop. Okay, let's look at the small loop. Here, we don't go through any EMFs. We're going with I2 through the 5 ohm resistor, and we're going against I3 through the 9 ohm resistor. So this is going to be a negative voltage drop. This is going to be a positive voltage drop. All right? So I have it sort of backwards right here. This should be negative, this should be positive, but we can reverse the two. That's absolutely fine. We basically see that the voltage drop between each of these is going to be equal and opposite. Okay? I2 times 5 ohms is going to be equal to I3 times 9 ohms. All right? And that really balances the voltage on top and the bottom. We knew that already. Solving for I2, we get that I2 is equal to I3 times 9 divided by 5. That means that I2 is equal to 1.8 times I3. Great. So now we have 3 unknowns, 3 equations. We all know from algebra. Once we have that condition, we have the possibility of solving this. So this, and this. I1 comes in, I2 goes out, I3 goes out. So what I'm going to do is I'm going to substitute this I1, I'm going to put this right there, and I'm going to put this right there. And that's going to allow me to basically convert my equation to all having terms of I3, and I1 and I2 have been substituted for. I solve for this, okay, I put all my I3s on the left-hand side, I put all my current on the right-hand side, do the algebra, and we find we have 3/10 of an amp. So once I know I3, I can solve for the others. I plug this, okay, into this equation to get I1, and plug this into this equation to get I2. So here's I1, I make my substitution for I3, I get 0.83 amps. Here's my equation for I2, make my substitution, and I have I2. And again, let's just check here. I1 is equal to 0.83. So I2 plus I3, I2 being 0.54, plus I3, 0.3, we're a 1/10 off. I'm sorry, we're a 100th off, but that's a roundup error. Yes, we get that I1 is equal to I2 plus I3, so it works. Okay? Again, we could have done this by taking these 2 parallel resistors and turning them into an equivalent resistor. Okay? Then they're in series with the 4 ohm We could then make that into an equivalent, find the current I1 from that, and then work backwards to find I2 and I3. However, I wanted to show you that Kirchhoff's rules actually works for even the simple circuits. Now we're going to go to something that we can't solve simply by reducing series and parallel resistors. This is a case where I have EMFs placed inside the circuit itself. Okay, now I'll look at this junction right here. We're going to have I1 coming in, I2 going in, and we're going to have I3 going out. I'll tell you right off the bat that I've actually picked the current in the wrong direction for some of these on purpose to actually show you how it works when you end up with a negative current. You actually have to switch the direction that the current is going. But again, it shows that this process is actually workable. So let's do this. We've got our first relationship. We've got this equation, I1 plus I2 equals I3. Okay? And now let's do some loops to get some additional equations. Yeah, we can do this junction, but we're going to get the same result, if we apply the junction rule there too. So I'll pick this loop right here. We're going clockwise. We're going to go through the 10 volt EMF, through the 6 ohm resistor, and then through this 2 ohm resistor. Now we're going with I3 this way, and we're going with I1 this way. So the IR here and the IR here are both going to be negative. We are going from negative to positive here, so that's also going to be positive there. So we get 10 volts minus the voltage across the 6 ohm. Again, I1 equals IR, I1 times the resistance of 6 ohms, through this one, I3 times 2 ohms. Again, remember, I3 is coming around this way. All right? That gives us a relationship between I3 and I1. We'll solve it in terms of I3 so we can substitute it back in our first equation. And I3 is equal to 5 amps minus 3 times I1. Okay? Let's do another loop. Now we're going to pick a different loop. We'll pick this top loop right here. Again, be careful with which way the current is going. This loop is going against the current here, okay, and going with I2, the current up here. So, be careful how things are going. This will be a positive voltage. We're going this way again. We're going from positive to negative. So this will be positive, this will be negative. Going this way, negative through this resistor, and negative through that EMF. So right off the bat, something's a little bit funny here. And this is telling us that we probably chose the wrong direction for our currents. Again, that's okay. We're going to come out with the right answer regardless, because the technique is just going to tell us that. So again, we set this up. The only voltage that's positive is through the 6 ohm resistor. That is I1 times 6 ohms. We get a 10 voltage drop through here, negative 14 voltage drop through here. Again, we're going positive to negative. We're going down voltage. And again, we're going with the current I2 through the 4 ohm resistor. Set all these up, get a relationship between I2 and I1. And see this big negative 6 amp right there? Probably indicates that I2 is actually flowing the other direction. Okay, fine, don't have to change anything. It still works for what we're doing. So we have this equation, we have this equation, and the equation we just solved. 3 equations, and now we're going to put them all together again. All right? Again, I1 plus I2 equals I3. I suspect I2 is going the wrong way. So I'll put this equation in right here, this equation in right here. That gives us one equation with I1. All right? Group like terms, put all the I1 terms on the left, put all the amp terms on the right. We then end up with this, divide both sides by 5.5, and that leaves us with I1 being 2 amps. So I1 was correct. It's 2 amps going in this direction. That one works. So with I1, I'll plug it into this equation for I2. Okay? I1's 2 amps, plug it in here. Oh, negative 3 amps. So again, I2 is negative 3 amps in this direction, which technically means, or more properly means, I2 is going this way. Okay? So 3 amps going this way. What about I3? I3 is 5 amps minus 3 times I1. We get 5 amps minus 3 times 2. Oh, this wasn't expected. Now we get negative 1 amp. That means I3 is actually going this way. So 2 and 3 were actually going up, okay? So I1 and I3 were coming into this junction and becoming I2. That's fine. We still get all the currents that we need. We still have all the directions. Here's another one, going very quickly. We have I2 coming in, I1 and I3 going out. There's our junction. That's usually the way you start these things. Pick one loop on the bottom, okay? There's quite a few things going on right here. We have I2 going this way. We're going with I2 and with I1. So our resistors are going to be negative, okay? Here we're going from negative to positive, so that's going to be a positive EMF. Here we're going from positive to negative, so that's going to be a negative EMF. Think about the flow. Think about the direction that the loop is going. We get this result right here. We get a relationship between I1 and I2. We find I2 is the opposite of I1. So what this is telling me right here is one of these two currents right here is in the wrong direction, but both are equal in magnitude. All right, two equations. We need one more to solve for everything. Now I'll choose a big loop on the outside. Here we're going with I1, so that's going to be negative voltage. Positive, negative, so that's going to be negative voltage. We're bypassing the center branch right here. We're going through the 2 ohm against I3, so that's going to be a positive voltage. So positive, negative, negative, put them all together. We get an equation for I3 with respect to I1. Okay, now we have 3 equations. Let's summarize what equations we have. This was the junction. This is the one that we did previously. This is the one that we just came up with. Just like we did before, we'll substitute in for I2. We'll substitute in for I3. That allows us to solve for I1. And again, we get the wrong direction. I1 is negative 1 amp. So I1 is actually going up this way. So I2, we did correctly. I2 is equal to the negative of this. I1 is going up. I2 is going 1 amp this way. We make that substitution there. And I3, just plug in I1, we get 2 amps. So, yeah, looking at the direction here, we had I2 going in, we had I1 going into that node, and I3 going out. Okay?